All right, so this example is, I don't know, something kind of cool, but let's say we want to estimate the temperature of the Earth, right? This has been, if you're interested in like the history of science, being able to estimate the temperature of the Earth is kind of something people have been trying to do for hundreds of years, mostly to sort of figure out how old the Earth is, because if you can figure out the current temperature and sort of how it's been cooling over time, you might be able to infer how old the Earth is, right? So people, for various reasons, have done that. For our purpose, I think if we could just get in the ballpark using radiation view factors, it'd be kind of cool. So what we have here is a three-surface problem. We have the sun. It exists at 5,800 K. It has a diameter that's very large. We have the Earth. Let's say we don't know the temperature of the Earth. We want to predict it. And the Earth is that number, 1.497 e to the 7th meters away from the sun. And then the third surface that we have is a sort of virtual surface. It's T3, which is space, 2.7 Kelvin. All right, plus or minus a few tenths of a degree. So this is our problem. What we're going to do is use view factors to compute the amount of energy that's going from the sun to the Earth, and then from that, estimate the temperature of the Earth. Some things we're going to assume here are that Earth is adiabatic. What does that mean? Again, that means that the net heat transfer to and from the Earth is zero. Is that really true? Well, not really, because the Earth still has heat that's generated from its core. So there's still some sort of net heat transfer out. And if the temperature of the Earth is changing over time, then that's not true, right? So it's not exactly true, but for our purposes, let's just assume that it is. Okay, so first thing we're going to do is let's represent this as a resistance network. So I'm going to take my three nodes, 1, 2, and 3. And I'm going to label them. So this surface here is EB2. This is the Earth. I said the Earth is adiabatic, so I'm going to draw a little adiabatic boundary here. Let's say up here, this is surface 1, so this is EB1. And I have some heat that's coming from the sun, which I could theoretically compute. So we'll call that Q dot 1. The resistance between the sun and the Earth, I'm going to call that RG from 1 to 2. I have a resistance from the sun to space. That would be RG 1 to, RG from 1 to 3. Space is at EB3. I have a resistance from space to the Earth. Let's call that RG from 2 to 3. And what else? So I know down here at this node, EB3 is equal to sigma T3 to the 4th, right? And I know T3, I told you it's 2.7. We don't know EB2, so let me just circle that. We don't know EB2. We can compute EB1, right? So we can compute that based on the temperature of the sun. So that is sigma T1 to the 4th. All right, what else here? I think that's good for now. So there's maybe two pathways that we have to worry about. So one is like what's directly going from the sun to the Earth, but then also like what is leaving the Earth going to space. And we could also maybe keep track of like what's going from sun, so we can keep track of what's going from sun to space. We can keep track of the heat transfer that's going from the sun to space via the Earth, right? Because we know that it's balanced. Okay, so what we're going to do now, so let's see here. So what I'm going to do is let's start by trying to calculate the emissive power. So emissive power, EB1, is equal to sigma T1 to the 4th. So that is, sigma is 5.67 e to the minus 8th times t to the 4th, so that's 58. 58. Come on, 5,800 to the 4th. So that happens to equal, let's see, 6.417 times 10 to the 7th watts per meter squared. By the way, if you're, like, it's easy to watts per meter squared of surface area emitted from the sun. All right, so you have 1 meter squared, that's what, 64 megawatts per meter squared emitted from the, it's insane, right? It's a big number. EB2. EB2, we just know that it's sigma T2 to the fourth, but we don't know T2, so we can't go further on that one. EB3, EB3, sigma T3 to the fourth. This one is 5.67 times 10 to the minus eighth times 2.7 to the fourth, which equals something very small, 3.013 times 10 to the minus sixth watts per meter squared. Very small, right? So in terms of like radiation that's coming from space and hitting the Earth, we can pretty safely assume that that's negligible, right? There's really not a lot of background energy, background radiation that's going to affect the temperature of the Earth. So this is the emissive powers. Next thing I want to do is just calculate the area. So there's a couple areas we need. These are pretty straightforward. We need the area of the sun, A1. That is, let's see, 4 times pi times the radius, which is d1 over 2 squared. Right, that's the surface area of a sphere. This is 6.07 times 10 to the 18th meter squared. And then A2, area of the Earth, that is pi times d3 squared, right, the 4's cancel out. Again, area of a sphere, this is 5.11, oh, sorry, yeah, I'll just write it, 5.115 times 10 to the 14th meters squared. Yeah, that's right. So pi d squared just comes from the fact that the d over 2, the 4 cancels out. Okay, so we have our areas. What next? So now we can compute some view factors and some resistances. Okay, view factor. So let's first think about the sun to the Earth. The view factor here, F from surface 1 to 2, is, we can compute this without like a library, because if we realize that the sun and the Earth are very, very far away from each other, the amount of radiation that's going to hit the Earth is basically the area of the sphere at the orbit of the Earth. Right? So you take like the distance from Earth to sun, and you make a sphere out of that. So it's that area, but then the fraction of light in that area that's going to hit the Earth is just the area of the circle occupied, like the projected circle of the Earth. Right? I'm not saying the Earth is flat, right? The projected circle of the Earth. All right, so all we need to do is calculate that projected area and then divide it by the total area of the sphere, and that's our view factor. So we can do that. That is, here it's pi times d2 squared over 4 over 4 times pi times, we'll call this distance, this one here, r, 4 pi r, capital R, squared. And that is a very small number, but it's important, 4.541 times 10 to the minus 10th. It's a fraction. So that is the fraction of all the sunlight that's emitted that goes to the Earth. Almost zero, but fortunately not. So we have that view factor. We could go through and say, all right, well, what's the view factor from the sun to the Earth, or sorry, from the Earth to the sun in reverse? Well, that would be just F12, the one we just calculated, times A1 over A2. We're going to say that this is approximately 0. Right? And why am I saying that? Well, first of all, we don't really expect that radiation from the Earth is going to have any appreciable impact on the temperature of the sun. Right? It's just not. So we can safely say it's 0 and not further consider any radiation in that direction. Okay, let's see. If we make that assumption, we can say F2 to 3. That's approximately 1. Right, so this is the view factor from the Earth to space. And we can say F13 is then equal to 1 minus F12 minus F22, right? F22 is 0. So we just have 1 minus F12. So we've computed all the kind of relevant view factors here. Okay, so then the last step is to compute the resistances and then come up with the energy balances. So I guess moving on here. So resistance, this would be R12, RG12. This is 1 over A1 F12. And plugging in the numbers, that's 1 over 6.07 times 10 to the 18th times 4.541 times 10 to the minus 10th. And that equals 3.628 times 10 to the minus 10th, 1 over meter squared. That's our resistance. R13 is 1 over A1 F13. That equals, that equals 1.647 times 10 to the minus 19th, 1 over meter squared. And then lastly, RG23 is 1 over A2 F23 equals 1.955 times 10 to the minus 15th, 1 over meter squared. Okay. So we have some resistances. We have filled those in. Now we can go back and do our energy balance and actually solve the equation. So first of all, we're referring back to our 3-node network. We had like the branch. Let me just flip back up here. Sorry, we have this branch that goes from 1 to 3 via surface 2. So if we can somehow estimate what's happening along that branch, we can then compute the emissive power EB2 and then temperature 2. So it turns out that like that branch directly from sun to space isn't that important to us. We just need to figure out the heat transfer along that other branch. So to do that, I'm going to note that the Q dot from 1 to 2 is equal to the Q dot from 2 to 3. Right? That's saying all the heat that's going from the sun to the earth is equal to all the heat that's leaving the earth and going to space. Right? So to write that out, it looks like just this. It's Q dot 1, 2 is equal to Q dot 1, 3. So using that idea, now I'm going to say that the rate of heat transfer from 1 to 2 is equal to the emissive power at 1, EB1, minus now the sort of the endpoint emissive power of that branch, which is EB3. EB3. And then I have to include the total resistance between those two things. Right? We've already sort of said that like what's happening in that branch to space is not important. You could include it if you want, but it turns out it's not important for this case just because of the assumptions that we made. So now our total resistance is RG12 plus RG1, this should be RG1 to 2, RG2 to 3. Okay, so we calculated out as 1.769 times 10 to the 17th. Let's see. So now what we can do is we have a heat transfer rate from the sun to the surroundings via the earth, right? Now we can just look at that one branch, that sort of one increment. We've solved for Q dot 1, 2. So let me just make a spot over here. So now we know Q dot 1, 2. We can say Q dot 1, 2 is also equal to EB1 minus EB2 over RG1, 2. Right? So this is now the specific branch that we've identified there. Sorry, I'm keeping you. Just give me another 30 seconds here. Because I know you really want to know what we're predicting for the temperature. So this is EB2. We solve this for EB2, gives us EB1 minus Q dot 1, 2 times RG1, 2. This gives us EB2 equals 346 watts per meter squared. So then that has to equal sigma T2 to the 4th. So we take the, divide by sigma, take the quarter root, and that gives us T2 equals 279.4 Kelvin, which is 43.3 Fahrenheit, when the actual temperature of the Earth is 59 Fahrenheit and rising. So, okay, takeaways, right? Not that bad, right? We're in the ballpark. All just using geometric view factors, okay? Thanks, everyone. See you on Wednesday.